Hi there, my name is Yichao. I'm from the Department of Computer Science at UCLA. This presentation is about pronunciation-attentive contextualized pawn recognition. So what is a pawn? Let me give you an example, which is actually one of my favorite pawn. I tell you a chemistry joke, but I know I wouldn't get a reaction. This is interesting, right? But what brings about the humor into the sentence? Okay, obviously the pawn word in this sentence is reaction. We can regard the chemistry as the pawn word's global context and wouldn't get a as its local context. Both local and global contexts are consistent with the meanings of the pawn word reaction. When reaction is interacted with chemistry, it represents chemical change. And when action is connected with the wouldn't get and joke, it means a kind of action or response. The two meanings of the same word create a humorous pawn when there's a clear contrast between the two meanings. And this is why we feel interesting. We named this type of pawn as homographic pawns. Homographic pawns rely on multiple interpretations of the same expression. Here's another type of pawns. We call them heterographic pawns. Similarly, the local and global contexts are consistent with the meanings of the pawn word. As we see from this figure, the boating is actually the global context and the sale is a local context. The store has its best is a local context. And the local and global contexts are consistent with the pawn word sale and sale separately. The SAIL sale links to boating, and while the SALE sale relates to the store has its best and ever. The same or similar pronunciation connects the two words, while the different meanings create funniness. In short, the heterographic pawns take advantage of the phonologically same or similar words. In this case, it is a to sale. Here are some other pawn examples. Don't go bacon my heart. Woohoo, it's Friday. And I'm feeling positive today. Obviously, the first two are heterographic pawns, and the third one is a homographic pawn. So in this paper, we tackle the pawn detection and the location tasks. The pawn detection is to determine whether a sentence contains a pawn word or not, while the pawn location requires to pinpoint the pawn word in the sentence. Some recent work deployed the word sense disambiguation methods for using external knowledge base like a WordNet. But these methods cannot tackle the heterographic pawns with distinct word spellings. And the knowledge bases only contain limited vocabulary. To resolve the issues of the sparseness and the heterographics, the word embedding provides flexible representations to model pawns. However, a word may have different meanings regarding its contexts, especially an influent meaning of the word might be utilized for creating a pawn. Therefore, static word embeddings are insufficient to represent words. In this paper, we propose a model called Pronunciation-attentive Contextualized Pawn Recognition. In short, it's PCPR, to jointly model the contextualized word embeddings and the phonological word representations for pawn recognition. We proved the effectiveness of different embeddings and modules in our model via extensive experiments. Okay, let's formulate the tasks. Suppose the input text consists of a sequence of n words. For each word, we have m different phonemes in its pronunciation representation. So for example, the phonemes of the word pound are p, r, n. Okay, and the first task is a pound detection. The pound detection task identifies whether a sentence contains a pound or not. Formally, the task is modeled as a classification problem with binary label. The second task is pound location. Given the sentence containing at least one pound, the pound location task aims to honor the pound word. More precisely, for each word, we would like to predict the binary label that indicates if a pound is that the word is a pound word or not. Here's the architecture of our framework. For each word in the input text, we will first derive two continuous vectors, including the contextualized word embedding and the pronunciation embedding. We know the context is essential for interpreting a word in the text. Hence, we propose to apply the contextualized word embeddings to derive the word representations. Here we choose bird to derive the contextualized word embeddings without loss of a generality. On the other hand, we look up a pre-trained phoneme embedding dictionary to achieve the phoneme representations. R represents the phonemes, and U is the phoneme embeddings. We then apply the attention mechanism to simultaneously identify important phonemes and derive the pronunciation embedding for each word. And in the equations, we can see that we first feed the phoneme embeddings into a fully connected layer and pass them by an activation function. Then we learn a context vector Vs and compute the attention scores alpha via a normalization. Finally, we achieve a pronunciation embedding for each word via a weighted summation of all the phoneme embeddings. Finally, a self-attentive encoder blends the contextualized embedding and pronunciation embeddings to capture the overall representation of each word, which will be used to determine whether the word is a pound or not. The whole sentence embedding can be derived by concatenating the overall contextualized embedding and the self-attentive embedding. A softmax function is applied to get a final prediction of the pound detection task. Since the pound detection and the pound location are both binary classification, we optimize the model with cross-entropy loss. The two experimental datasets are the largest publicly available benchmarks that are used in the existing studies. Because the pound of the day dataset does not provide the location of the pound words, we only work on pound detection task on this dataset. One thing I want to mention here is that SAM-Eval 2017 dataset contains pounding and non-pounding jokes and other short texts, and also some other short texts composed by the professional humorists and online collections. So we assume that the genres of the positive and negative examples should be identical or extremely similar. We adopt the precision, recall, and F1 score to evaluate both pound detection and location tasks. The first 6 baseline models are SAM-Eval task participants. These methods extract the complicated linguistic features to train rule-based and machine learning-based classifiers. The sense model incorporates word sense embedding into a recurrent neural network. And the CRF model captures linguistic features such as post-tags, anagrams, and word suffix. The SOTA model jointly models 2 tasks with recurrent neural network and a CRF tagger. We also implement the simple version of our model CPR, which exploits only the contextualized word encoder without considering the phonemes. In the results, we observe that the PCPR dramatically improved the pound location and detection performance compared to the SOTA models join and CPR per precision, recall, and F1 scores. In the heterographic pattern recognition tasks, we see PCPR outperform CPR in large scale. We think that's because by applying the pronunciation-attentive representations, different words with similar pronunciations are linked, leading to a better pinpoint of the pattern word for the heterographic datasets. And an interesting observation is that the pronunciation embeddings also facilitate the homographic pattern detection, which implies the potential of a pronunciation for enhancing the general language modeling. So this is actually consistent with another work that improved the quality of word embeddings by introducing the pronunciation features. Here are the experimental results on the PDD datasets. We compare our method with another 4 baseline containing rule-based and neural network-based models. From the result, we can see that our CPR and PCPR models outperform all 4 baseline models. The results further prove that the contextualized word embeddings can be capable of distinguishing semantic contradictions among the context of a word with multiple meanings. And on the other hand, the phonological embeddings can be pronunciation. Embeddings can be intuitively useful to recognize identical pronounced words for detecting the heterographic patterns. We also conducted an evaluation study on the Semivel 2017. The results show that all these components, phoneme embeddings, self-attention encoder, and phonological attention module are essential for PCPR to recognize patterns. To visualize how well the self-attention mechanism works for pattern recognition, we plot the attention weights to denote the connection between keys and queries. From the figure, we can see that the busy, Zhou, boarding store are highly related to the 3 pattern words: harried, lying, sale. We also have detailed case studies and error analysis in the paper. So to give a conclusion, in this paper, we propose a novel approach, PCPR, for pattern recognition by leveraging the contextualized word encoder and modeling the phonemes as the word pronunciations. We would love to apply the proposed model to other problems such as general humor recognition, irony discovery, and then sarcasm detection as a future work. We also plan to employ the pronunciations to tackle more NLP tasks, considering the performance lives on the homographic patterns.